Ну, я по-английски буду, потому что если придет китайец, чтобы не переключаться как-то. Okay, let me start. So first I need to address a minor correction. So Sergey was right. There was some mistake in defining anti-holomorphic representation, which is just to draw a bar a little bit shorter. So anyways, we had this representation of V lambda. So this is a representation of SL2C and it's holomorphic. But we look at this group as real Lie group. So we also have anti-holomorphic representation V lambda. And the action here, so it is V lambda as vector spaces. And we need to say what is an action of G if I have an element V from V lambda bar, then action is just, well, I act as by G bar on V, and this is action in V lambda, just in V lambda. So I wrote something like bar over here as well, which is of course not correct because identity doesn't go to identity. And also I said that the involution that we defined there commutes with this action, which is true if we define it like that. It was. Okay, so then we started talking about supergeometry. And we talked about superarranged spaces and superspaces. And in short, superspace, it's what? It's a pair, topological space, and sheaf of super rings. And so this is sheaf of super rings. And we want every stock to be local, right? So maybe this. So for any x from x, the stock is a local ring. So this is a reminder. And we actually also defined what are morphisms from one superspace to another. Sorry, OX here, Y, OY here. So we have the following data. So if I have morphism phi, then it consists of a continuous map from X to Y, and also well, for any open set V in Y, we have a pullback. Also, we have to put it by hands or define it by hands. So phi star V, this is from O. So this is from O V OY of V to OX of phi tilde inverse of V. And this should commute with restrictions. So that was all said last time. So now we're ready to say what is a supermanifold. Almost ready. So we need to define what is the local structure. So we need to consider the superspace that will denote by this. So in Vardajan book it's just this, but it can be confused with just a superspace, real superspace of this superdimension. So which is not the same as what we define it now. So I guess I will use maybe this notation. So what is this? As topological space, it's Rm, and well, the sheaf of super rings, well, it's something that I will denote as C infinity Mn, where C infinity, so where Mn at, well, sections of this sheaf. These are just smooth functions on Rm tensored with, well, so to say, well, free anti-commutative algebra generated by n elements, theta n. Well, we had this notation, right? So they're just free algebra generated by relations theta I, theta j equals to negative theta j, theta I. That's it. Yes, I think it should be here. No, but so I say that it is a superspace. Theta, антикоммутирует. Все. Ну, и с собой тоже, то есть θ в квадрате 0. Okay, so I said that it is superspace, so Stokes should be local. So I at least I need to, you know, spell out what is a maximal ideal here. Maximal ideal mx. This is well, this is all classes with representative f, which is well, f is an element in here, right? So I can write it down as follows: f tilde of x plus sum fi theta I. So here it's clear what I mean, right? So I here is just a, you know, set of symbols, and well, theta to the power I is just theta I1, theta I2, theta IK, and they can repeat. Well, they can repeat, but doesn't. Then it's just 0, so they cannot. But here I want the size of the set to be at least 1. Right, because without any thetas we already take it into account in the term. And so if I write f, well, any f can be written like this. So condition is that f tilde at, well, maybe, so this x is fixed, right? So my f is f of some y, right? And the condition is that f tilde of x is 0. So that's my description of the maximal ideal, unique maximal ideal inside here. It's just you can see that if anything is not in this ideal, then it's inversible. And this basically proved that it's a unique maximal ideal. All right. So let me now go ahead and define what is a supermanifold. A supermanifold is a superspace well, with underlying topological space X and a sheaf O, such that the following thing happen. First of all, I need to care a little bit about topology of X. So X should be, well, the topology should be as for just usual smooth manifold. So it's Hausdorff and second countable. And secondly, well, it's locally isomorphic to this, right? So how do I put it? So for any point X in our topological space X, there exists an open neighborhood of X. So this is open and contains X, such that, well, and maybe let me also throw into here an open subspace of Rm for some m, and this is open, such that, let me go here, such that, well, U, O, U, so this means that I restrict this shift to U, this one, is isomorphic to V, and then C infinity M N, well, I need to write it like this, V. And isomorphism in the sense of morphisms of superspaces. So we have homeomorphism between U and V, and well, we have corresponding pullbacks. All right. So maybe let us see some examples. So examples. Well, first one, it's not interesting for now, but will be more interesting later. GLMN. So this is this is, so let's say, submanifold inside R m squared plus n squared 2 mn. Sorry, and I need to put parentheses everywhere here. Right? Yes. According to my notation. So, so this is an open subset. So it's a restriction of this super manifold to its open subset. Which open subset? Well, I need to write. Well, I should think of. Well, I should think of this as matrices A, B, C, D. So really underlying topological space is just this matrix and this matrix. So this just usual topological space, which is just R m squared plus n squared. And well, I kind of think of the rest as odd part. Then the open subset inside here that I need is the following: the determinant of A times the determinant of B is not 0. Okay. So it's just, it's just this is super manifold, and this is open subset, which is also super manifold. Well, topological component is open subset. Ничего, да, это просто как x, это просто r m квадрат плюс n квадрат. Ну, это, значит, там нет таких матриц, как бы, грубо говоря. Да, то есть это просто картинка, чтобы как бы думать про это как про блоки. Вот, можно просто как бы хорошо, можно, если не нравится вот про эти бейтсы забыть вообще, но по крайней мере А и Д у нас есть, правильно? Вот, и я про них так говорю. Вот, хорошо. Извиняюсь, да. And maybe more interesting example where we don't have just the one chart. Well, I will of course call this neighborhoods with this isomorphisms charts as usual in smooth manifolds. So another example where I don't have just one chart, but maybe I need more, which will be projective superspaces or super projective spaces. I don't know. You can just add super to any place here. So projective superspaces. Okay, so notation will be, so we need to choose choose a field. So let me choose C. So C, let's talk about CPMN. So projective superspace CPMN. What would that be? Okay, underlying topological space is just CPM. And well, so if I have so let me take some V. So now I need to define a sheaf, right, of super vector spaces, super rings. So So let me, and this shift should give me super ring for every V which is open inside CPM. So let me fix some. So let V inside CPM be open subset. And so let me actually take and lift it to Cm plus 1. So I consider V prime, which is an open, well, it's inside Cm plus 1 without 0, right? Such that, well, it's just pre-image with respect to the projection, right? So it's a lift of yeah, but yeah, so lift of V with respect to just projection, natural projection from Cm plus 1 minus 0 to CPM. Then I would like to define, well, let me consider the following super algebra. So I'll denote it as AV prime. So this is just C infinity on V prime. Well, this is basically C infinity Mn on V prime, right? So, so tensor C theta 1 theta n minus, explicitly this. So let me, it's just a notation, but then C star acts on it. Right, it acts. It acts, of course, on C infinity of V prime, right? V prime is of, well, on V prime it acts because it's a lift of V, right? So more explicitly, what's the action? The action is the following: T acts on something like this, Fi of x theta I, as follows. So it's just sum over I Fi x, well, T inverse of x times T to the power negative the size of I, then theta of I guess, well, this group is commutative, so I actually can take maybe, so left and right action is the same, so, but I guess this inverse here is just to be consistent with action of any group, not necessarily commutative. So we have such an action, and I'm just defining, so then define O of V, so super ring correspond, so sections, which are sections of our sheaf O that we're defining on V, is just AV prime. So all fixed elements with respect to such action. So all invariant, well, all fixed elements. All right. Then, so what's the point here is that maybe I can write now in formulas is that, okay, on usual CPM, well, I have charts and I glue one chart to another, right? By, multiplying all the coordinates by the same number, all right? So here I have more coordinates, so I have to multiply them as well. So that's the only kind of difference and what's going on here. So so what are our charts here? So the charts, UI, I goes from 1 to m plus 1. And so UI is just, as usual, chart for CPM, x1. So in homogeneous coordinates, so these are all points where xi is not 0. All right. And well, then UI, of course, and with restriction of O to UI, is of course isomorphic to R Mn. And isomorphism is just, you need to take, well, just usual isomorphism, you need to take the corresponding xi to 1 by rescaling, right? And this will give you the coordinates, right? So just, I don't know, even, is it clear? Just usual, like in CPM. The only thing is that I have to rescale, well, when I act, I have to act on that as well. So this is the only change with formulas. Maybe let me just go through an example rather than writing. So let me consider CP11. Just to simplify life a little bit. So, okay, so I have U1 and U2 in this case, right? So these are underlying topological spaces for my charts over there. And then, okay, if I have, well, f of u, well, if I have like f of u which is inside, well, which is a section on u1, for example, well, it looks as follows. F of u is just, some f0 of u plus f1 of u theta. So any section looks like this. It's nothing else really. Okay, and then of course if I have another section, it also looks like that. Maybe I need like another notation for coordinates. For example, u prime or v. I don't know what. Yes, I think v and maybe theta prime on the other chart. All right, but the formula for the other, for any section, like it looks like this always. So how do I go from one chart to another? So let's see what's the difference here. So I have now homogeneous coordinates, and they now look like this. So I have z, I don't know, 0, z1, and then theta. So theta is now also homogeneous coordinate. Again, this, maybe you look at this as a picture to understand what's going on. Right. And so how do I go, what is this U, a relation of this U and this theta, by the way, to those coordinates? Well, I need to divide, so I need, okay, maybe I need to go Z1 and Z2 to match this 1 and 2, right? And so what is this U? I need to make Z1 to be 1, right? So this is the same as 1 Z2 over Z1, and then, well, actually I need to divide theta now by Z1. Right. Maybe let me denote this by 1, because like this is theta in first. So this is like a homogeneous theta, right? Which is really, you should think of this as you know, something that help us to see how we should glue charts together. This is really coordinate on U1, like odd coordinate. Right, and then this is my U, and this is my theta 1. Right. Now let me go to the other chart. Right. Let's okay. So let me write down. So if I have, I don't know, G of V is inside O of U2. Well, I would like to write it as G0 of V plus G1 of V, and then theta 2. All right, so the same thing. What are the relations between coordinates on different charts? That's what I'm trying to do. Okay, so now I need to make, and suppose this is a point in intersection also. So I need to divide by Z2 to make this 1, right? I will have Z1 over Z2, and then 1, and then theta over Z2. But yes. So then this guy is V, right? And this guy is theta 2. And my relation now is that on intersection, I have that V equals to U inverse, right? And theta 2 is theta 1 U inverse. All right? So that's how I glue two sections together on intersection. All right? So I just replace, well, I take section, for example, here. Well, I can express the other way, but let me take this section. Then make this substitution. And this gives me a section here. So this is how it works. And the message here is that not only V works like in just usual projection space, but also thetas. And that's like an odd part of all of this. All right? All right. So this is it. I think I'm done with examples for now. So now let us, okay, so next remark that I want to do, and you also might ask, how supermanifolds are different from alternating vector bundles. And actually they are almost the same. So the difference is that you have more morphisms between supermanifolds than between vector bundles. Okay, let me fix this in writing. Right, so suppose that I have vector bundle E over X. So this is vector bundle and actually line bundle. Over, well, suppose it's line bundle. Then having this line bundle, I can consider supermanifold, which I denote as E flat. I don't know, that's Verdrajan's notation. I guess it's or B or flat, whatever. Okay, so underlying topological space is X, and sheaf is the sheaf of sections sheaf of sections. Sorry, why line bundle? It's not sorry, I take my words back. It's just vector bundle. Otherwise, not so interesting. My odd dimension would be just 1, right? But I want my odd dimension to be just the same as the rank of this E, right? So rank E, let it be, I don't know, n, right? And dimension of X is m. So this is sheaf of sections of this vector bundle. So I claim that this is supermanifold. I don't know whether it requires, but no, this is sheaf, okay, because it's sheaf of sections, right? Locally, what's going on? Locally, it's trivializable, right? So therefore, you have the functions there, right? They look as functions, well, sections here, right? They look as follows, right? They look as functions, some function on X, right? So, well, what is, I don't know, what is an element? So suppose that I don't know how to explain it better, but it just follows from the fact that this algebra is isomorphic to this algebra. That's it. I don't know, it should be simple and clear. And I really nothing, like if you look at it like for a minute, nothing has to be checked here. So this is really a supermanifold. And well, V is actually is a fiber here, right? So this is Ex over some point X. All right. And so the question is whether all supermanifolds, they are just isomorphic to this one. And well, there is a big theorem, non-trivial, which we will not prove, that actually the answer for smooth supermanifolds is yes. Actually, all smooth, so let me formulate it as theorem. So any smooth supermanifold is isomorphic to some E flat well, to semi-flat. That's it. But then also is some facts. Not that I know how to prove them or any counterexamples, but it's not, this theorem no longer true if we have analytic supermanifolds or complex supermanifolds. So not true for analytic or complex supermanifolds. But okay, these are some very general facts, but even with this theorem, it's still important to think rather, so we still have difference, but the difference is in morphisms. And the morphisms, they actually can mix odd and even variables if I have a supermanifold, but morphism between such things as vector bundles, they don't. So actually we have more morphisms. This is the main idea, and let me illustrate this idea and actually describe how morphisms works. Well, we defined what are morphisms, but can we really see how morphisms work locally? So we actually can, and we start with example. So illustrative example. So let us describe morphisms from R, okay, 1, 2. 1, 1 is not so interesting, but 1, 2 is already interesting. And R, from R1, 2 to itself. So let's look at this example. Okay, so I know that if I have a morphism from this to this, this means that I have a couple of things. Well, first, so phi is the following data. So I have continuous map, and I have, well, natural morphism, which gives me all the pullbacks. So phi tilde here is just a smooth map from R to R, really, in this case, right? So, okay, and then how would, so okay, so phi star, well, it's enough to define how it works on sections, like on global sections, because then everything else here is just restriction of global sections, right? So let me describe how phi star, it's a morphism from C infinity R, tensor R theta 1, theta 2, minus to itself. So this is a super commutative algebra, and this is homomorphism of should be homomorphism of super commutative algebras. And okay, so I have in particular here I have an element just x. So x is a coordinate on R, which is also a function, right? In here. So this. Let me consider x as an element in here. So how phi star would act on x? So I know that it is a morphism of super algebras, or okay, super rings. So in this case, superalgebras as well. So it should be, so this is an even element. So the result also should be even. Well, arbitrary even element here, it's what? It is just an element in here, right? But I claim, so, okay, I claim that phi star of x should look like this. It's just phi tilde of x with this phi tilde. Plus, and then since it should be even, I also have option to just multiply theta 1 times theta 2, right? So this will be something phi 1 of x, theta 1, theta 2. In general, right, I should have here some function phi 0, right, plus this, right? So this is what restriction that this preserves parity gives me, right? Nothing else. So I claim that this component should be exactly phi tilde of x. And this follows from the locality of phi star. Remember, morphisms, they also should be local, so they should map maximal ideal to maximal ideal. So I claim that the fact that here should stay phi tilde of x follows from the fact that phi star should be local. Let me show that. Ну да, нет, это я неправду сказал. Ну, здесь, наверное, нужно действительно, можно вместо R писать какой-нибудь U, ну и все то же самое будет говориться. Ну или как бы пример того, как морфизм, ну да. In principle, yeah, so I said that indeed the restrictions, the sections are not only restrictions from global. No, you're right, this is not correct. But what I'm saying is that you can replace this R with any U and just say the same things. Right. Okay, let me erase this. So let me try to show that here indeed we should have phi tilde of x. All right, so it's just, I need to take what? So let me take x minus phi tilde, well, let me fix, so now x is a function, it's an element of this ring, right? But x 0 is just a constant. Right, it's a really real number. X0 is just a number. Arbitrary, yes. Yes, so let me take x minus phi tilde of x0. And let me look at it. So at stock of this, right, at phi tilde of x0. Then this guy is inside, this is of course is inside M of phi tilde of x0. Right? And let me apply phi star to it. Well, I guess I should, I'm abusing notation a little bit, so phi star is a pullback, but also it's induce a map on stocks. right? Which I just act on representatives. All right. I think. Well, I have to put phi tilde of x0 here, but let me not do this. It's just too much fun for subscript. Right. So let me apply this to this. Then, well, this is just by definition. It's just a pullback of x minus. But this is just really a constant, right? And so, and this should map 1 to 1 because it's a homomorphism of unital rings, right? So really what I get is again the same constant. But then this point moves to x naught. That's just how, just by definition, how we induce map from like how pullback induces a map on stocks. But look, this guy should be inside, since it's a local map, this should be inside phi, inside m x0. But this means what? This means exactly this. It means that, well, this is for any x0. Right? So, for any x0, if I write phi star of x equals to sum phi 1 of x plus phi 2 of x theta 1 theta 2, right? The fact that this is inside m of x0 means that phi 1 of x0 is phi tilde of x0 for any, well, this minus this should be 0, right? This is for any x0. And so therefore phi 1 should be phi tilde. Okay, so this is really the fact that here I have phi tilde is really follows from the requirement for phi star to be local. Then after this being said, let me just, because we're working with example, let me simplify things and let me just put, so assume that this is just identity transformation, and this phi 2 at the moment, just to tell the message, it's not really matter as far as just it's not 0. Let me put it 1 just. So phi 2 is just 1. Then I have phi star of x is just x plus theta 1 theta 2, right? But you see, so now arises the problem. So if I do it like this, right? So okay, I took some, very important, of course, element of this ring, but can I? Well, of course now I can also define phi star of theta. Maybe not define, but see what it should be. I don't know. It should be an odd element, right? So it should be something like what notations I have here. Doesn't really matter. Phi, I don't know, 1, 1. Well, here is either theta 1 or theta 2, right? So theta I. I don't know. So it should be just linear combination of thetas, right? With some coefficient, which for some reason I denoted like this. It just because it should be odd. But okay, so these are kind of our coordinates, and so I'm trying to see how phi star should act on coordinates. Well, what are my options? But if suppose that that I fix some how it acts on coordinates, but can I just extend it to any to any element from this ring? So the problem is with this guy, because, well, if I take something from C infinity of R over there, if it's a polynomial in X, then okay, I just replace X with this. But if it's just some smooth function, what do I do? You see, there's something should be said here, and yeah. So what does it mean? So we need to force some rule, actually, and well, this rule will be natural. I just try to formally expand. So I substitute and formally use Taylor series with respect to theta's, and this Taylor series will just will be cut at some point, and this will be just my definition of how I substitute. So I just define so suppose that I have f from C infinity of R. If I have some theta's, it's clear what to do, because in theta's you always have polynomial, right? But suppose that you have this, then what would be phi star of f? So if it's polynomial, it's clear. If it's not a polynomial, or anything, I just might define it like this. So this is just by definition f of x plus f prime of x, theta 1, theta 2. That's it. Well, I use Taylor series at x, where this is formal Taylor series. Right? Then, of course, I might try to use this definition, but then I have to check that it is indeed works well. For example, it's a homomorphism of rings, but basically that's everything that we need. And it also works well. Of course, it boils down to just our usual rule here if we have a polynomial, right? So it's consistent. Well, you can just go ahead and check by hands that this is homomorphism of rings. I will not do this, but maybe I say how to check it in more general theorem that I'm about to state. But just follows from the fact, basically, that this derivative satisfies Leibniz rule. That's the only idea here. Right, but not only this is some working way how I can define the morphism, but this is a unique way. So let me show that. So this is a unique choice. So uniqueness of the choice, star. You see, and actually the check that this is homomorphism actually will be clear now, So, all right, what can I do? I have phi star of f. I know that this is an odd element. Sorry, f is even element, so I have to have even element. So it will be, again, this will be f because of locality and our choice of phi tilde. So if phi tilde is any, this would be a pullback of this function by phi tilde. All right, plus, this is just the plus something which I denote by something that depends on f, so some linear function, linear or, well, linear, yes, of course, theta 1, theta 2. So the question is, what is this guy? So this is locality again of phi star. Just the same argument. So I claim that actually L of f should be a derivation. No, it's a check, of course. So, well, phi star should be linear, so therefore it's linear. But also we have to have that phi star is a homomorphism. So I should have this, right? Phi star of G. Right. Well, I just get put it inside and see. Well, on one hand, maybe it's just very simple. So on one hand, it's fg plus L fg theta 1 theta 2, right? But this guy is just f plus L of f theta 1 theta 2. And the g plus L of g theta 1, theta 2. Then I open up the brackets and I see what? Fg plus L of fg plus Fl of g theta 1, theta 2. And you see that then L should be a derivation. L is derivation. And, well, there is not so much derivations on R. So really, L is up to some constant. It's d over dx. But what is this constant? We know that L of x is 1. So I act on this by x. So C should be 1, right? That's it. So it's a unique choice, really. Well, once I fix how it acts on my coordinates, this is a unique choice. So again, message here, there are two messages. One is that morphism, so we actually built a morphism, right? So we built some morphism that mixes even and odd elements. That's message number one. Message number two, it is uniquely defined by its action on coordinates. And so now we can formulate it in the for example, well, I mean, mix in the sense that, of course, even goes to even, right? But you can compose even out of odd. So this never happens. This never happens in vector bundles, for example, right? So thetas, they are, I don't know, they're elements of the exterior algebra on a fiber. You cannot go to coordinates by any means. Ну, я как бы составил четные из нечетных. Так. General theorem. Okay. For future references, I call it theorem 1. So I was talking about homes from R12 to R12. Now let me replace this 1, 2 to Mn and I don't know, Lk. And I can formulate the following then. For any y1, yl in C infinity M n R M 0. And again, yes, I'm putting RM here, but I can replace it with this theorem doesn't change if I replace here sections to some sections on open neighborhoods of RM. And Xi1, Xik from C infinity Mn Rm1. So these are even elements. I fix L even elements and K odd elements. Okay, I have some language issue here. Let me put it let y's will be even and xi odd, and let x1 x m and theta 1 theta n be coordinates like super coordinate. On well R Mn. Then sorry, x and theta should be coordinates not on Rmn but on Lk. So here L and K. Then there exists a unique morphism phi from R 1, 2 sorry, from Rmn to Rlk such that phi star of xi is yi, and this is for any I from 1 to L, and phi star of theta j is xi j for any j from 1 to k. Okay. Right. So let me. So we just will follow ideas of our example to prove this. So we have 15 more minutes. Okay. Yes. How many? I don't know. We finish at 11:30, right? Да? Окей. Хорошо, вы меня... 5 минут осталось. Ну, давайте тогда и не будет... Ну, давайте тогда, может быть, докажем existence. Вот, а uniqueness на следующий. Хорошо. Это хорошо, что вы меня поправили, чтобы я не увлекся. Да. Правильно. Вроде только здесь, да? Ну, как мы изначально как бы обозначали там КМН, супер векторное пространство, супер размерность МН. Это вот не это. Потому что реально как топологическое пространство это R в степени M. То есть, ну какая-то, я не знаю, у Вардраджана и то, и другое одинаково обозначается. Вот. Ну, давайте пытаться как бы эти скобочки ставить. Вот. Ну, то есть концептуально это разные вообще-то вещи. All right. So proof of existence for now. So first, so we need to do what? Define continuous map and define pullbacks, right? So continuous map. Well, locality dictates us that what we should do. So the map should be from Rm to RL, right? And so, okay, so I have, suppose that I have coordinates x1 prime, xm prime, and theta 1 prime, theta m prime. So these are coordinates on R, M, N, right? Then yi, I can write yi somehow in this coordinates. I don't know, yi, some yi tilde, right, of x prime. So these are elements. So y's are elements in this superring, yeah, even elements, right? So actually, my y I can write it like this: some yi tilde of x prime plus something with thetas. Also might be here, I of x prime theta I, where I here greater or equal than 1, right? But and forget about this. I only need this part for phi tilde. And so phi tilde, for phi tilde, I define that it maps x1 prime, well, point with these coordinates, m here, right? M and here n. To the point with these coordinates, y1 tilde, x prime, blah, 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 y1 tilde L of x prime. So that's my phi tilde. Then pullbacks. Pullbacks is enough, again, from we see from example, but now it's clear. In general case, if pullbacks is enough to define on elements on C infinity of RL. So if I have F from C infinity here, right? Well, pullbacks should work. Pullbacks, of course, should be defined on any open subset. But okay, just replace this with any open subset. Right, so I do globally just to keep track of this index, but in principle, this should be defined for any open subset. So I just define phi star of F then as follows. So it's function, I don't know, phi star of F. Anyways, I don't need this. So it's a sum over set of indices. And here I take, multiple derivative of F, but pulled back by phi tilde of X prime. And derivative with respect to X primes. All right. And then I should put psi I in here. Right. So this should match. This should match this definition, kind of. Right. So we generalize this. So we really take. Sorry, something doesn't work, right? So it should be not xi I, right? Some different power should be here. I guess it should be phi star of. No, it's okay. It's very good. Xi is theta 1, theta 2 there. Xi is pullback of that. Sorry. Xi. No, it's not good. Should be not xi here, but y. Right? Still not. So yeah. All right. So my formulas, I need to correct them. And since we're out of time, so what it's clear how to correct, right? So I take pullback of X, right? I need to, okay, I have everything in here, right? Do I? Yeah, so I need to define, I need to take this guy, right? And define, I don't know, let me define this as Y capital I, right? And so here I should put Y capital. Right, because I differentiate, so I, yes, yes, I think so. Okay, let me check. So I think this is how. But okay, we will return to this. My initial formulas in my notes, I think not correct. But let me check. I think this formula should work, but maybe not. Да, и, соответственно, дифференцирую я по штрихованным, правильно? Да, я подставляю. Ну, а, кстати, может быть и нет. Значит, я дифференцирую по тому, от чего зависит f. Правильно? То есть f у меня зависит на самом деле от L, значит, от L штук. То есть и от одного, там индексы от 1 до L идут. Вот. И, соответственно, я смотрю, ну, то есть это действительно тут координаты вот, ну, хорошо, надо подумать, как это исправить. Давайте я подумаю. Тут как-то не очень формула пока работает. Значит, идея понятна. То есть я беру вместо x итых, вставляю y иты. И потом, но в y иты у меня чего-то есть. Да, мне нужно придумать что-то вот, что я делаю с этой частью. Да, а и как раз у меня бегает вот это от 1 до L. Нет, мне кажется, что все окей. Да. Окей, все, давайте тогда завершаться.